Hello, this is the first unit from TTIC, Toyota Technological Institute at Chicago, course 31230 on fundamentals of deep learning. This unit is going to be an overview or a timeline of the history of deep learning up to the present. When I used to give this class, I used to spend a lot of time trying to convince people that we're now entering a Moore's law of AI. And by that, I mean that significant progress is being made every year. Now, after teaching this course for 6 or 7 years, I don't think I have to convince anyone of that anymore. I think most people believe that dramatic progress has been made. So in this unit, I'm just going to review what has happened over that time period. And I'm going to start very early, a long time ago. In 1943, McCulloch and Pitts introduced the linear threshold unit. Now, the linear threshold unit remains, or a version of it, remains the central workhorse of deep learning. The idea is you take a linear combination of inputs, pass it through a threshold function. If it passes the threshold function, the signal continues, and it's based on the anatomical structure of actual neurons from 1943. In 1962, there was a very well-known approach to machine learning called Hebbian learning. And Rosenblatt introduced this. It made a big splash in 1962. We're not going to talk about that in this class. In 1969, Minsky and Papert wrote a book called Perceptrons. And this book had a bunch of theorems, mathematical theorems, that certain things could not be expressed by linear threshold units. Now, they ignored the possibility of stacking linear threshold units on top of each other, so-called deep neural networks. Even though they had ignored that, these theorems put a kind of damper or slowed down progress in neural networks. And symbolic approaches based on symbolic logic, dominated artificial intelligence in the 1970s. Okay, so in 1980, Fukushima in Japan introduces the neocognitron. Now, this is a form of convolutional neural network. So this is the real origin of CNNs from 1980. In 1984, Leslie Valiant introduced a formal concept called PAC learnability, probably approximately correct. And this started an enormous amount of research in learning theory, especially focused on generalization guarantees. What can you guarantee from results on training data about results on new data? And Valiant won the Turing Award, the Nobel Prize of Computer Science, in 2010 for this work, much later. So in 1985, Hinton and Sejnowski introduced the Boltzmann machine. We're not going to be talking about that much, but again, that was a major development in the neural network world in 1985. In 1986, Rumelhart, Hinton, and Williams demonstrate the empirical power of backpropagation. Now, backpropagation itself dates back to 1961, but it wasn't a prominent tool until this time, 1986. In 1997, this is still before the deep revolution, Jürgen Schmidhuber introduces the LSTM, the long short-term memory. This is a form of recurrent neural network or gated neural network. And we're going to be talking about those in significant detail. What's interesting about this is it made a big impact 20 years later or 15 years later. So this was something that was very important in the early days of the modern era. And I'll talk about the modern era in a bit. In 1998, Jan LeCun draws attention to convolutional neural networks. It had been developed by Fukushima, but it was LeCun's paper that really got more attention in the community. It's called LaNet. In 2003, Yoshua Bengio was the first person to develop a neural language model. So this is, again, still well before the deep revolution, but it was the first neural language model. Very simple, very unsophisticated, nothing like the transformer. Okay, most people date the current era, the current rapid progress in deep learning to this 2012 development called AlexNet. There was an ImageNet competition to try to develop a challenging data set, millions of images with 1,000 different categories. This was, at the time, by far the most challenging image classification data set in existence. And there was a competition at the prominent computer vision conference, CVPR, and a deep neural network destroyed the competition, just dominated the field. And that was kind of strange for me because at that time, the dominant system in object detection was a system that was developed at TTI Chicago, the so-called deformable part model. And all of the vision systems at that time were based on the deformable part model until AlexNet. And AlexNet killed the deformable part model. So we lost our prominence. About the same time, 2012, Google speech recognition as done in Google applications converted to deep networks, to deep learning. And both of these groups, AlexNet and the speech recognition, came out of Jeff Hinton's lab in Toronto. In the next few years, progress on image classification was dramatically fast. There was dramatic, quick progress in image recognition. In 2014, neural machine translation appears. Ilya Sutskever, who's one of the founders of OpenAI, gave a talk at NeurIPS, the main machine learning conference, in which he had some great statements about this neural translation system. He said, "Minimal innovation for maximal effect." I love that quote because it was saying you can take a very simple model, very simple ideas, and if you have enough power in your deep learning architecture, deep learning can do all the hard work for you. You don't have to develop a complex model. You develop a simple model and let the deep learning do all the interesting things. It was a great talk, an interesting development. A lot happened in 2014. Variational autoencoders are introduced. This remains a central method in machine learning. Diffusion models are a version of variational autoencoders. Generative adversarial networks appear, GANs. GANs are a huge development. They remain significant, although of somewhat declining importance. We'll certainly spend a lot of time talking about GANs. Graph neural networks appear. Graph neural networks are particularly important for predicting the properties of molecules, where the organic molecule can be viewed as a graph on atoms. So in 2014, we're also continuing to see dramatic improvement in vision and speech recognition. So in 2015, Google converts to machine translation, converts to deep learning in machine translation. And there were whole groups at Google that have been doing machine translation for decades that were told they had to convert to deep learning, and they were not happy. Batch normalization appears. We'll be talking about batch normalization. Residual connections appear. We'll be talking about residual connections. Diffusion models appear. Now, this was a very early paper on diffusion models. Diffusion models did not enter the mainstream for several more years, but the first paper appears in 2015. So in 2016, which is already 8 years ago, reinforcement learning is to develop AlphaGo, which defeats Lee Sedol at Go. This was huge. Go was supposed to be a game that AI would not be able to solve for decades. And the idea that you just hit it with deep learning and it just works was really very surprising and really contributed to the idea that deep learning is really changing the game in AI. In about a year later, 2017, AlphaZero was developed. Now, AlphaZero is different from AlphaGo in that it learns completely through self-play. There's no imitation learning. There's no, it never reads games and what moves were made in those games. It's not being trained by human moves. It's just playing itself, given the rules of the game, and within a month or a few weeks becomes superhuman. This is astounding. Also in 2017, a big splash was made by something called unsupervised machine translation. Here you take a corpus of English text and a corpus of German text, and you don't give it any translations. You just give it the English text and the German text, and it studies English and it studies German, and somehow magically it learns to translate English to German. Not state-of-the-art translations, but reasonable translation ability. And it's called unsupervised because it's not given any translation pairs, no pair of English and the corresponding German, just a corpus of English and a corpus of German. And this was really shocking. A new form of GAN was developed called progressive GANs. This came out of NVIDIA, Keras, and this was really shocking progress. And we'll see some pictures of this later. Okay, 2017. Now this is getting to be more like 5 years ago, 6 years ago. The transformer appears. Now, when I first saw a talk on the transformer, I was excited. Not everybody believed it right away, but I did. So the transformer, of course, is a huge development, and all of language processing and lots of, essentially much of deep learning is converted to a transformer. And of course, we'll be talking about that in detail. In 2018, unsupervised pre-training, particularly in language models, significantly improves a broad range of NLP tasks, natural language processing tasks. And of course, we're going to be talking about that. Contrastive learning is formulated. This is a particular approach to pre-training foundation models that we will be talking about also. AlphaFold comes out of DeepMind, and AlphaFold revolutionizes protein structure prediction. So this is a problem that was a core problem in molecular biology for the last 50 years, and nobody could solve it. And the idea that we can apply deep learning and actually determine the three-dimensional structure of a protein from its sequence of amino acids, that's the protein folding problem, really shocked the molecular biology community and has led to very rapid progress in proteomics, in the understanding of what the human proteins or all animal proteins are and what they do. Okay, I mentioned progressive GANs. This is a timeline of GAN image generation. So a generative adversarial network is a generative AI system trained in a certain way, in a certain adversarial way. It's a generative adversarial network, or GAN. And this is just a timeline. They were first developed in 2014. And by 2018, they were developing pictures that were really indistinguishable from human faces. These people do not exist. There was a famous headline showing pictures developed by progressive GANs about this time, and the headline would be, "These people do not exist." This is not a photograph. It's made up out of whole cloth. That's an English phrase. Making it up out of whole cloth means you just invent it. So GANs made a lot of progress at this time, not just in generating faces. Faces are the easiest thing to do with generative in image generation, in generative image AI. Anything that's other than faces was much harder to do. So when you see faces from a generative model, you're supposed to not be impressed because faces are easy. At least the modern thinking is faces are easy. This is a timeline of what's called class conditional GANs. So you would say, this is the class flower. So these are all pictures of flowers. So at this time, GANs were only effective if you had a particular subject matter that was specific for the GAN. So this is GANs on dogs. And these class conditional GANs gradually got better. So by 2018, they were generating pretty good pictures. Here are these pictures, GAN synthetic images, generated images from this time period, 2018. Okay, now I said that variational autoencoders were another architecture, and we're going to be studying those in detail. I've always felt that VAEs were more interesting, more principled, and ultimately should perform better than GANs. But during this time period, GANs were making a lot of progress and VAEs were not. So these are VAEs from 2015, about the time VAEs were introduced. Now, faces are supposed to be easy. You just saw the faces that were being produced by GANs just a few years later. But then in 2019, suddenly VAEs got a huge advance. So these are VAE faces. These are people that do not exist, generated by variational autoencoders. So this made me very happy because I always liked variational autoencoders. These are images, class conditional images from 2019. They're very different from the class conditional images that are generated by GANs. These are GANs. These are VAEs. Note that in the VAEs, the background is kind of matte. So this is interesting differences, but the subject is very good. 2019, natural language understanding. So this is a time when preconditioning, just training language models on language, predicting the next word, or at this time period, there was a lot of interest in a system called BERT that instead of predicting the next word in a sequence, which is what you hear about now, autoregressive language generation, this would mask out a word and predict the missing word from both ends, from the context. Anyway, it was pre-training language models. So you pre-train a language model to predict the next word or to predict some masked word, masked language modeling. And then you take that pre-trained model and you fine-tune it on some downstream task. So there was this benchmark that was created called the General Language Understanding Evaluation, or GLUE. And it consisted of maybe 10 different tasks. One of them was entailment. Does this sentence imply that sentence? One was parsing. The hardest one was called the Winograd problems. And the Winograd problems involved determining the referent of a pronoun, like he or it, where the referent depended on this, just switching one word. Like, I'll think of an example, but there was this benchmark. And at this time, 2019, basically what happened is that all of these benchmark problems got basically solved essentially to human performance levels. And they were solved by pre-training on language and then fine-tuning on whatever the task was, entailment or parsing or the Winograd problem. So an example of a Winograd sentence is the trophy did not fit in the suitcase because it was too large. It refers to the trophy. Or if I said the trophy did not fit in the suitcase because it was too small, the it refers to the suitcase. So if I switch large and small, the meaning of it flips. And it feels very semantic. So you would think that getting that pronoun right would involve semantic understanding. And that was certainly Winograd's intention. But even the Winograd problems got solved essentially to human performance, very close to human performance by pre-training language models. Okay, wave to vec. This is something based on contrastive learning. And the idea here, or the question here, is when people, babies, start to learn language, the first thing they have to do is hear the phonemes, the phonetic components of the words. So somehow they're being exposed just to speech, and they're learning symbolic tokens, phonemes. And then they're learning how to, words are strings of sounds, and you have discrete sounds like tokens. So wave to vec is a system that will take just pure sound, no training, no sound and transcription, and learn phonetic units. They call them pseudo-text units automatically. And it's closely related to something called vector quantized variational autoencoders. The big progress in variational autoencoders came when people started doing vector quantization. And that vector quantization is analogous to what happens when you learn the phonemes of a language. And they showed that by pre-training on 1 hour, by pre-training on language and learning this phoneme system, these pseudo-text units, they could reduce the amount of sound transcription pairs. So they want to do speech recognition. They want to be able to take sound and output text. And they demonstrated that by learning the phonetic units automatically from pure sound, the amount of transcription you need, the amount of data, which is sound paired with the text, can be reduced by a factor of 100. So it greatly reduces the amount of labeled data you need. So now we're up to 2021. This is a generative spoken language model. So what is this? It's related to wave to vec. You take sound, you use vector quantized VAE to translate the sound into these pseudo-text units. And then you use an autoregressive language model to model the sequences of these pseudo-text units. And then you can generate sound, right? You generate a sequence of these pseudo-text units, and then you can synthesize that into sound. So instead of a language model that generates text, this is a model that takes sound and learns to generate sound. So it's surprising to me that just being trained on sound, it can output sound that is intelligible speech and even has certain, recognizes certain grammatical properties. Okay, now 2021, CLIP, contrastive language image pre-training is called CLIP. This is a contrastive method. What it does is it takes pairs of images and text. And the idea that you can train on pairs of images and text is fundamental to current image generation from textual descriptions. This was the first time that this really worked effectively. You take a large corpus of images and text, and you can get that off the web, either by looking at image captioning or looking at pointers, URL designations of image files. You get a name for the image file. You can scrape off the web a large collection of pairs of image and text. And then you use this contrastive learning method to find an embedding. You're going to embed the language into a vector, and you're going to embed the image into a vector. And the idea is this vector that you can match either language in or image into is a shared conceptual space that's representing language, or it's representing the image, a kind of shared conceptual space. We'll talk about this in a lot of detail, but this shared conceptual space, this ability to translate language and images into this shared vector space, supported a large class of applications. So in particular, you can support image captioning. I can give you an image, I can map it into this conceptual shared space, and then I can take this vector in this conceptual shared space and generate text from it, because I've modeled the relationship between the vector and the text. So this allows me to do image captioning. Image captioning means you take an image, you put it up, you represent it in this shared space, and then you decompress it, you translate it back into text, and that serves as an image caption. And then you can use this to classify images. So I show the system an image like this, and then I take a bunch of possible classifications. It's either guacamole or ceviche or various tuna tartare, and I want to know how to classify this. I consider all of these sentences, and I say which one is most likely, according to the language model generating from the representation of this image, which of these sentences is more likely. And you find out that the guacamole is more likely, and then you can use that fact that this sentence is more likely to classify this as guacamole. And then what you can do is, because CLIP is trained on image text pairs in general, it's not just trained on AlexNet, say, it's trained on this open domain scraped web set of image text pairs. I can use it in any domain. So here's the AlexNet domain, and the CLIP classification is matching the AlexNet state-of-the-art classification. But if I go to different domains, this general CLIP approach remains strong while AlexNet falls apart. AlexNet fails. So this becomes domain independent. Okay, so I said that scraping this big corpus of image text pairs supports lots of different things. And eventually people sort of stopped using CLIP and just trained directly on generating text from images or images from text. And in 2021, January 2021, DALL-E 2 appears. Let me back up. In 2021, they're still using CLIP. This is still based on CLIP. They haven't yet gone to direct image text relationships. And the other thing that DALL-E did in 2021 was use a diffusion model. And later in this course, we're going to spend a lot of time talking about diffusion models because they're the latest thing. They're the biggest recent architecture to overtake the field most recently. So this is DALL-E 1. DALL-E 1 was not based on diffusion models. This is just based on a kind of VQVAE, and it's generating these cartoon-like images. Here's DALL-E 2. This was based on diffusion models, DALL-E 2. And this was the first model that could generate really high-quality images from basically an arbitrary text prompt. So this is something that would have been viewed as absolutely crazy sci-fi even 5 years ago, even 5 years before this. So this was really astounding. Okay, July 2021, Codex appears. So this is the first time people were trying to use language models to write code, to write computer code. So there's a nice demo of Codex from this era where Ilya Sutskever and a couple other researchers are just telling the system to build an app, and they're showing you the app run as they're telling them in English what they want the app to do, and Codex is writing code for the app. That demo is a little misleading. I think it was, they prepared it ahead of time, and it doesn't really work that smoothly. The automatically generated code often still has bugs. But GitHub Copilot appeared about this time, and many programmers used that to get an initial version that they then debug for their code. And in that setting, this is a very, it does improve the productivity of programmers. Okay, in January 2022, chain of thought appears. So chain of thought is a way of prompting language models. So this is the way this works. This is question answering. This is question answering in number problems. So Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And the answer is 11. This is a prompt. You're giving the language model this as a prompt. You're saying, continue this line of text. So you're asking ChatGPT to continue from here. And the way to continue from a question is to give an answer. That's the pattern in the prompt. So if you just give it this prompt, it says the answer is 27, which is wrong. But in the prompt, if the answer in the prompt contains a chain of thought, 2 cans of 3 tennis balls each is 6 tennis balls. 5 plus 6 is 11. The answer is 11. Then when the model tries to solve this problem, it lays out its reasoning. It's been prompted to state its reasoning. And when it's prompted to state its reasoning, its accuracy improves. It actually demonstrates some reasoning, and then it gets the right answer. So this is called chain of thought prompting. And it turns out that I think it's a group from the University of Tokyo. It's a Japanese group who discovered that all you have to say is take it step by step. And if you say take it step by step, the language model will introduce steps of thought and get more accurate answers, more accurate conclusions. And this is a very general prompt. So prompt engineering has become a big deal. Everyone who uses language models now puts a lot of energy into their prompts. I just wanted to mention this. This did not get a lot of press, but in 2022, DeepMind demonstrated in simulation very effective humanoid soccer play. This is a big deal to me because I've always felt that even in simulation, the reinforcement learning methods for robotic control have not been very good. This is a significant advance in robotic control in simulation. Okay, March 2023. This is like a year ago now. GPT-4 is unveiled, and it's a major advance in language modeling and what we can do with language models. And of course, people are now very concerned about AI safety, and a lot of people are wondering when artificial general intelligence will actually arrive. And not everyone is convinced that we're on the verge of AGI, but certainly people are thinking about it and talking about how to make the machines friendly as opposed to taking over the world. So people are talking about AI safety. These slides are from the past fall, from 2023. So this is what was happening at that time. DALL-E 3 was just announced. I'm thinking now that there hasn't been any really new dramatic developments that I've seen sort of in the past year. And I'm wondering if this phenomenon of dramatic developments every year might slow down now, might have slowed down in the past year. Anyway, I just want to talk about some open problems, some things that cannot be done. There's the math zero problem. So the question here is, can you do for mathematics what AlphaGo and AlphaZero did for chess and Go? Could you, in principle, build a system that just by exploring mathematics on its own, just by kind of self-play, could learn to do mathematics at a superhuman level? And the reason this is an interesting question is because mathematics itself can be formalized as a game. The foundations of mathematics, the fundamental axioms are understood, they can be written down. So the game, in some sense, the rules of the game are well defined. But there's not been any real progress on this problem. It remains extremely hard. So that suggests that there's something we don't really understand yet. A simpler problem is auto-formalization, reading mathematics papers and translating them into formal notation. And that's related to the proof assistant problem. Can you build a system that's just an assistant to mathematicians, just can crank out low-level details that are tedious for the mathematician to do? Automated mathematics remains challenging. We haven't had a lot of progress on automating mathematics. So I also want to make a distinction between advancements in applications and advancements in architecture. So what's happening in deep learning is the same ideas, convolutional neural networks, skip connections, normalization layers, the transformer, contrastive learning. All of these ideas seem to be domain independent. They apply all over a broad class of applications, from molecular biology to game playing to language processing, to automatic programming. But when we consider Moore's law, I want to make a distinction between progress on the applications and progress in our understanding of architecture. And in this class, what I want to focus on are the general ideas, the architectural ideas. So here's just a list of core architectural ideas. We go back to 1943, we have the linear threshold neuron. Then, in the 1980s, the neocognitron was developed, CNN. Backpropagation is a central idea. Recurrent neural networks, or RNN, are a central, not quite as popular now, but were a central architectural idea. Neural language modeling, variational autoencoders, generative adversarial networks, GANs, graph neural networks, normalization layers, residual connections, diffusion models. These are all sort of architectural ideas. Just to continue this list, reinforcement learning is a very general idea, it turns out. The transformer, unsupervised pre-training, vector quantization, contrastive learning, and prompting. These are all very general. I'm going to end there. And in the next unit, we're going to start real mathematical content. We're going to start what I call the fundamental equations of deep learning that sort of govern all of these ideas and all of these architectures. One of them being the linear threshold unit, and the other being cross entropy. So we're going to start with real mathematics at the next unit. So thank you very much.